Welcome to GitKudu's study channel. In this video, let's learn the electronic components and devices, subject introduction, and also about resistors. Electronic components are the fundamental building blocks of all electronic devices, from simple circuits to complex computers. These components manipulate the flow of electrons to perform specific functions. These can be broadly categorized as passive or active components, depending on their ability to control the flow of electrical current. Passive components cannot generate energy and instead either consume, store, or regulate it. Resistor, capacitor and inductors are the passive components. Resistor, which limits or restricts the flow of electric current. Capacitor, which stores electrical energy in an electric field to stabilize voltage and smooth out fluctuations. Inductor, which stores energy in a magnetic field, often used for filtering. Active components are semiconductor devices that can control and amplify the flow of electrical current. Active components require an external power source to operate. Examples of active components are diode. It is a semiconductor device which allows current to flow in only one direction and is used for tasks like converting alternate current to direct current. Transistor. It will act as a switch or amplifier for electronic signals and electrical power. Integrated circuit. IC is a microchip that combines many components, like transistors and resistors, into a single, small package to perform complex functions. Difference between active components and passive components. Active components will require an external power source to operate, whereas passive components does not require external power source. Active components are capable of amplifying, rectifying, or controlling electrical signals, whereas passive components are incapable. Active components are delivers or produces energy into a circuit, whereas passive components stores, dissipate or absorbs energy within a circuit. Examples of active components are transistors, diodes, and integrated circuits. Passive components are resistors, capacitors and inductors. In circuits, active components are used for signals processing, whereas passive components serves as foundational support, managing and stabilizing energy flow. Electronic devices are those devices, from simple circuits to complex computers, built by connecting passive and active components, often on a printed circuit board, PCB. Some common examples include digital circuits, the foundation of computers that operate on a binary system, ones and zeros, sensors, devices that convert physical phenomena like light or temperature into electrical signals, smartphones, laptops, and appliances. These advanced devices use a combination of different electronic components, especially complex ICs, to perform their functions. Now let's learn about resistors. Resistor is a passive electronic component with two terminals that are used for either limiting or regulating the flow of electric current in electrical circuits. It does this by introducing resistance, a property. Measured in ohms, it is made of copper wires which are coiled around a ceramic rod, and the outer part of the resistor is coated with an insulating paint. The main purpose of resistor is to reduce the current flow and to lower the voltage in any particular portion of the circuit and in protecting other components from damage. Resistors are found in nearly all electronic devices, ranging from simple household appliances to complex computing and communication systems. Resistance is the property of a material that opposes the flow of electric current through it. This opposition is due to the collisions between the moving electrons and the atoms or ions within the material. Resistance, R, is quantitatively defined by Ohm's law as the ratio of the voltage, V, applied across a conductor to the current, I, flowing through it. R equals V divided by I. The SI unit of resistance is the ohm. Resistivity is an intrinsic property of a material that quantifies how strongly it opposes the flow of electric current. It can be calculated by the following formula, where R is the resistance, A is the cross-sectional area, ρ is the resistivity, L is the length of the material. Conductors, examples copper, silver, will have low resistivity, whereas insulators, examples rubber, glass, will have very high resistivity. Classification of resistors. There are different types of resistors, which are mainly classified into 1. Linear resistors, 2. Nonlinear resistors, 1. Linear resistors. In linear resistors, the value of resistance changes based on the applied temperature and voltage. These linear resistors are again classified into fixed and variable resistors. In fixed resistors, the value of resistance is fixed and cannot be changed. These are mostly used in fixed circuits because the resistance value is fixed. Mainly used in electronic circuits where a stable or fixed resistance is required. For example, in voltage dividers or current limiters. Fixed resistor follows Ohm's law, which states that voltage, V, is directly proportional to current, I, and resistance, R. There are different types of fixed resistors. They are carbon film resistors, wire wound resistors, metal film resistors, thick or thin film resistors, SMD resistors, variable resistors. In variable resistors, the value is not specific and can be changed and can manually adjust the value of resistance by using the dial knob of a screw. It is also known as potentiometer, having 2 connecting wires instead of 3. Variable resistors are mainly used in applications where resistance needs to be variable. For example, in volume controls or sensor applications or radio receiver. There are the different types of variable resistors. The primary types variable resistors are potentiometer, a 3-terminal device used as a voltage divider, example, volume controls. Rheostat, a 2-terminal device for controlling current flow, example light dimmers, motor speed control. Trimmer, trimpot, a small, preset potentiometer used for circuit calibration. Digital potentiometer, an electronically controlled version for digital systems. Applications range from audio volume control and light dimming to motor speed adjustment and position sensing in joysticks. 2. Nonlinear resistors. In nonlinear resistors, the value of resistance changes significantly with changes in voltage or current in an electrical circuit. This indicates the relationship between voltage and current is not proportional and it do not follow Ohm's law. The resistor values change according to the temperature and voltage applied in the circuit. Mainly used in applications where resistance needs to be changed based on the applied voltage or current, i.e., like voltage regulation or precise control. There are different types of nonlinear resistors. They are thermistors. Thermistors change their resistance based on temperature. They are used extensively as temperature sensors or current limiters. NTC, negative temperature coefficient, thermistor. PTC, positive temperature coefficient, thermistor. Varistors. Varistors change their resistance based on the voltage applied across them. Photoresistors. Photoresistors change their resistance based on the intensity of light striking their surface. Specifications of a resistor and its importance. The specifications of a resistor define its function and limits. Understanding them ensures the correct component is selected for a specific circuit application. Resistance value, omega, the primary value defining the current opposition, crucial for implementing Ohm's law, that is V equals IR, to limit current or create voltage drops. Tolerance, plus or minus %, the allowable deviation from the nominal resistance, important for precision circuits, example, measurement equipment, where exact values are critical for performance. Power rating, W, the maximum heat the resistor can safely dissipate, essential for safety and reliability to prevent overheating and component failure. Temperature coefficient, ppm per degree Celsius, measures resistance change with temperature, determines the circuit's stability across different operating temperatures. Maximum voltage, V, the maximum voltage that can be applied across the terminals, ensures the component does not experience dielectric breakdown in high voltage designs. Stability and noise, defines long-term reliability and unwanted signal generation, critical for sensitive applications like audio or measurement instrumentation to maintain signal integrity. Physical size or mounting, determines the physical fit, relevant for manufacturing and design constraints, example, fitting on a PCB. Necessity of preferred values in resistors. The necessity of preferred values, E-series standards, in resistors ensures manufacturing and logistical efficiency. Key reasons for using a standardized, limited set of values. Efficiency and cost, reduces production complexity and inventory costs for manufacturers and suppliers. Availability, ensures components are readily available off the shelf for designers. Tolerance overlap. Values are spaced logarithmically so that, when accounting for a resistor's tolerance, every possible ohmic value is covered by an available standard component. Design convenience. Engineers can easily select standard components that approximate their calculated values, simplifying the design process. Resistance value by using color code. Resistor color coding is a standardized system of colored bands used to indicate a resistor's resistance value, tolerance, and sometimes its temperature coefficient, because the components are often too small for printed text. A common mnemonic to remember the color order, black to white, is B.B. Roy of Great Britain had a very good wife. Black 0. Brown 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7. Gray 8, white 9, gold has plus or minus 5% tolerance. Silver has plus or minus 10% tolerance. Bands convey information. Each color corresponds to a digit, multiplier, or tolerance percentage. Reading direction. Resistors are read from left to right, typically starting with the band furthest from the center or the thinner tolerance band. Common types: 4-band resistors, 2-digit bands, 1 multiplier band, 1 tolerance band. 5/6 band resistors, more digits for precision, plus tolerance and potentially a temperature coefficient band. Example: to calculate resistance for the following resistor with bands brown, black, red, gold. Brown equals 1, black equals 0, red equals multiplier equals 100, gold equals plus or minus 5%. Answer equals 1000 ohms plus or minus 5%, or 1 kilo ohm plus or minus 5% tolerance. Example 2. Find the resistance for following bands: green, blue, black, brown, red. Green equals 5, blue equals 6, black equals 0, brown equals multiplier equals 10. Red equals tolerance equals plus or minus 2%, so the answer is 560 into 10 plus or minus 2% equals 5600 ohms or 5.6 kilo ohms plus or minus 2% tolerance. Difference between various resistors: they are carbon composition, made from a mixture of carbon powder and a ceramic binder. They are inexpensive but have low precision and are sensitive to temperature changes. Film resistors consist of a thin or thick layer of conductive material, carbon, metal, or metal oxide, deposited onto a ceramic rod or substrate. They offer better precision, stability, and lower noise than carbon composition types. Wire wound resistors, made by winding a resistive wire, like nichrome, around an insulating core. They are known for high power handling capacity and accuracy, often used in high power applications. Thin film resistors, made by vacuum depositing a thin metallic layer onto ceramic. They are more expensive, but highly precise and stable. Thick film resistors, made by screen printing a paste onto ceramic. They are cheap, common, but less precise. Surface mount resistors, tiny, rectangular resistors designed to be mounted directly onto the surface of printed circuit boards, PCBs, commonly used in modern electronics due to their small size. Wire wound potentiometer. A wire wound potentiometer is constructed with a resistive wire, typically a nickel chromium or manganese alloy, wound around a non-conductive core like ceramic or plastic. A wiper, connected to a rotating shaft, slides along the exposed windings to vary the resistance between the middle terminal and either of the two fixed end terminals. The core is often coated in an insulating layer, with a narrow window or a movable contact element exposing a section of the resistance wire for the wiper to touch. Constructional details of wire wound potentiometer. Resistive element. A high resistance wire, such as nickel chromium, nichrome, or manganese, is wound around a non-conductive core. This forms the main resistive component of the potentiometer. Core. The core provides the structural support for the resistive wire. It is often made of ceramic, which is heat resistant, but can also be plastic or metal. Insulating coating. Window. The core and wire are typically covered in an insulating material like glaze or varnish. A narrow window is left in this coating or a special movable contact is used to expose a segment of the resistive wire, allowing the wiper to make contact. Wiper or sliding contact. A movable contact, known as a wiper, slides along the exposed resistive element. This contact is connected to the middle terminal. Shaft and housing. The wiper is moved by a rotating shaft that passes through the center of the core. This shaft is connected to the external control knob and is housed within an outer casing that encloses the internal components. Terminals. There are 3 electrical terminals. 2 are fixed and connect to the ends of the resistive wire, while the third is the variable connection point for the movable wiper. Carbon potentiometer. A carbon potentiometer is a 3-terminal variable resistor consisting of a resistive element made of carbon, a wiper, sliding or rotating contact, and 3 terminals. The primary components and construction details are as follows. Resistive element, track, a carbon film coated onto a non-conductive base, ceramic or plastic. Wiper, a sliding metal contact that moves across the track. 3 terminals, 2 fixed terminals connected to the ends of the carbon track, and 1 variable terminal connected to the wiper. Actuator, a shaft or slider used to move the wiper and adjust the resistance. The movement of the wiper along the carbon track changes the resistance between the wiper terminal and the end terminals, thereby controlling the output. Difference between wire wound and carbon potentiometer. Wire wound potentiometer offer higher precision, power ratings, and stability, but they are more expensive and not suitable for high-frequency use due to inductance. Carbon potentiometer cheaper and suitable for high-frequency use due to lower inductance, but they have lower power ratings, precision, and stability. Need for tapering in potentiometers. Potentiometer tapering is needed to match the component's electrical output to human nonlinear perception, like sound volume, or specific circuit requirements. Logarithmic taper or audio taper matches the human ear's logarithmic perception of sound and light intensity, providing smooth, even control over the entire range. Linear taper provides a direct, proportional relationship between physical position and electrical output for applications like position sensing or calibration controls. Tapering improves user experience by spreading the useful control range across the entire mechanical travel of the potentiometer. Rheostat. A rheostat is a two-terminal variable resistor used to control the flow of electric current in a circuit by changing the resistance. Construction and working of rheostat. A rheostat has a coil of resistive wire on a frame. It has 3 terminals, but only 2 are used for a standard rheostat function, one fixed terminal connected to one end of the wire, and a second terminal connected to a sliding contact, wiper, that moves along the wire.
A rheostat works by changing its resistance, which controls the flow of current in an electrical circuit.
Varying resistance. The resistance in the circuit is determined by the length of the resistive wire between the 2 terminals being used. To decrease resistance, the wiper is moved closer to the fixed terminal, which shortens the length of the resistive wire the current must pass through. To increase resistance, the wiper is moved further away from the fixed terminal, which increases the length of the wire, thus increasing the resistance. Controlling current. According to Ohm's law, resistance and current are inversely proportional, I equals V by R. Lower resistance. A shorter wire length leads to lower resistance, which allows a greater amount of current to flow through the circuit. Higher resistance. A longer wire length leads to higher resistance, which restricts the current flow. Applications of rheostat. Light dimmers adjust the brightness of incandescent lights by changing the current. Motor speed control control the speed of electric motors in devices like fans. Heating elements regulate the temperature in heating devices. Laboratory experiments used in scientific and educational settings to control and measure electrical quantities. Effect of temperature on resistance. Conductors, example, metals, resistance increases with temperature because atoms vibrate more, hindering electron flow. They have a positive temperature coefficient. Semiconductors and insulators. Resistance decreases with temperature because more electrons are freed to carry current. They have a negative temperature coefficient.
Temperature coefficient of resistance. The temperature coefficient of resistance is defined as the change in resistance per unit original resistance per degree change in temperature. It quantifies how sensitive a material's resistance is to temperature variations.
Symbol in units. It is typically denoted by the Greek letter alpha and is measured in units of per degree Celsius. Formula. The resistance of a material at a given temperature can be calculated using the following formula. RT equals R0 into 1 plus alpha delta T, where RT is the resistance at temperature T. R0 is the resistance at a reference temperature T0. Alpha is the temperature coefficient of resistance. Delta T is the change in temperature T minus T0. T0. The sign of the temperature coefficient depends on the material type and indicates how its resistance behaves with temperature. Conductors have positive temperature coefficient, that is resistance increases with temperature. Examples of conductors are copper, silver, gold, aluminium. Semiconductors have negative temperature coefficient, that is resistance decreases with temperature. Examples of semiconductors are silicon, germanium, carbon. Insulators have negative temperature coefficient, that is resistance decreases with temperature. Examples of insulators are glass, wood, rubber, varnish. For special alloys, temperature coefficient is nearly zero and its resistance also constant. Examples of special alloys are manganese, constantor. Solve this question using above formula. The resistance of a conductor at 20 degrees Celsius is 3.15 ohms, and at 100 degrees Celsius is 3.75 ohms. Find the temperature coefficient of resistance alpha for the material. Thermistor. A thermistor is a temperature-sensitive resistor used for measuring and controlling temperature or protecting circuits. Working principle. Its resistance changes significantly with temperature. NTC, negative temperature coefficient, resistance decreases as temperature increases, most common. PTC, positive temperature coefficient, resistance increases as temperature increases. Applications of thermistors, sensing, used in appliances, ovens, refrigerators, medical devices, automobiles, and HVAC systems. Circuit protection, function as self-resetting fuses, PTC, or inrush current limiters, NTC, in power supplies and battery packs. Sensistors. A sensistor is a heavily doped semiconductor resistor with a positive temperature coefficient, PTC, meaning its resistance increases linearly as temperature rises. Principle, mechanism, increased temperature causes more thermal agitation in the material, hindering the flow of charge carriers and increasing resistance. Characteristic, provides a stable, nearly linear change in resistance over a specific temperature range, unlike standard PTC thermistors which have a sharp transition point. Applications, temperature sensing, used as precise temperature sensors. Temperature compensation, stabilizes other electronic circuits, like oscillators and transistor bias networks, against temperature drift. Leak detection, utilized in specialized equipment for detecting minute hydrogen leaks in industrial settings. Over-temperature protection, integrated into motors and transformers to monitor for overheating conditions. List common faults in resistors. The most common faults in resistors are a change in their resistance value, often leading to an open circuit failure, and, rarely, a short circuit. Key faults include 1. Open circuit, most frequent failure, acting as a complete break in the circuit. 2. Drift in resistance value, the value changes over time, affecting circuit performance. 3. Short circuit, resistance drops to near zero, rare. 4. Physical damage or burnout, visible damage from overheating. 5. Sulfurization, chemical reaction causing increased resistance or an open circuit. 6. Electrode separation, connection failure due to mechanical stress. 7. Increased noise, intermittent contact in variable resistors due to wear or dirt.